Yeah, recording started. Yeah, now do you see my screen?
Yes, sir. Now we can see.
Oh, okay. Sorry, I just forgot. Yeah, so in the last class, we have seen a program, a recursive function for printing all permutations of n different things, which in that example, we have taken as 1, 2, 3 up to n. Okay, so let us now generalize this. All permutations of, I again want to print and count something, A1, A2, A3. So these are, let's assume, some objects, maybe all positive integers. But unlike this previous thing, we will now allow repetitions. In fact, this problem was raised by some of you. For example, I may think about all possible permutations of, let's say, 97, 31, 22, 97, 97, 30, 31. Okay. So this is not necessarily 1 to n. There can be arbitrary numbers. Moreover, I am allowing repetitions like this. Okay. So by a slight modification of the code that I have written in the last class, we can achieve this. Okay. So let us see what is the basic idea behind this. So suppose that what we have done earlier, up to this point we have fixed, and then from I to n minus 1, we are looking at all possible permutations of the remaining part. Okay. So here I have something, 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 and so on. And what I was doing, I was bringing everything at this position. Okay. The first position starting from the ith position, and then recursively finding all possible permutations of I plus 1 to n minus 1. Okay. Eventually, when I reaches n minus 1, there is nothing else to be done because there is only one, I would say, element, and it permutes in a unique way. This is how recursion proceeded. So now what I do, I will again bring things here, but before doing that, I will take some cautions. Let's say the remaining things are 2, 5, 1, 9, 2, 9, anything, maybe again 9. Okay, and this part we are anyway not handling. This is already fixed. Okay, so earlier what I was doing, I was bringing 2 in this position, then I am bringing 5 in this position, then 1, then 9, then again 2, 9, 9. The point is that, so initially this, I am making a recursive call on this 2. Okay, keeping it like this. 5, 1, 9, 2, 9, 9. Okay, and this part is as before, but this time I have included up to this. Then what I was doing, I was swapping this 2 with 5 to 1, 9, 2, 9, 9, and making a second recursive call with this. Okay. And after this recursive call returns, I am once again restoring it to this form. Then I was bringing 1 to this position. This is the third element, 2, 5, then 1. So that is done by swapping 1 and 2. 5 will remain as usual, 9, 2, 9, 9. Make a third recursive call. Then 9, I will bring 9 here. 5, 1, 2, 2, 9, 9. Make a recursive call on this remaining part. Okay. Now, if I once again bring this 2 in this position, then I am essentially, if I once again want to bring this 2 in this position, then I am essentially in the same position as this. Okay. Similarly, if I want to bring this 9 to this position, I am essentially in the same position as this. Agree? So since 2 has already appeared in the array, I will no longer consider this to sit in this position and make a recursive call. Similarly, 9 has already appeared in the array, so I have already checked this. Okay, 9. And then I have found all permutations of this remaining part. So this is already considered because of these 2. This is considered because of this 9. This 9 is considered because of this 9. So somehow I have to avoid these calls, because otherwise I will generate permutations in a duplicate manner. Okay, so duplicate things will be generated. So the idea is swap with AI, or maybe I would say swap AJ with AI if and only if AJ occurs for the first time. Is this idea clear? What I am going to do?
Yes, sir.
Okay, good. So let us write today's version. Permutation, let's say general. Any numbers with permutations allowed, with repetitions allowed. Std I will write the main function first. Int n, and let's say 100 element array. I actually need another I. First, read from the user n, and then for I equal to 0, I less than n plus plus I scanf %d and a I. So these are arbitrary integers, and maybe even negative. Okay. Then what I will do, let's have some count. C. So perm, or maybe permute, to have the same name. Permute A, number of elements is n, and I will start permuting at index 0. Right? Do you need anything else? A is the array, n is its total size, and start permuting from index 0. Okay. Okay. And just I will print these many permutations. That is the count. And then the customary exit 0. Okay, so this will return an integer value permute int array, total size n, and index I. Okay. So I need to use two indices J and K. And I also keep a count here. Okay. And if I is equal to n minus 1, then I will simply print this permutation. J equal to 0, J less than n plus J printf percent 3D maybe, give small numbers. AJ then print the new line and finally return 1. Okay, so that was exactly the same as in the last example. Remaining thing will be slightly different. So I will set count equal to 0. Okay. Now for j equal to I, j less than n plus j. What I was doing, I was earlier under the assumption that the elements are different from one another. I was simply swapping I with aj. So let me write the previous code. Okay, so I need a temporary variable t. This was what I was doing earlier. Now, before doing this, I have to do something else. So let me restore this last week's version. And this count plus equal to permute a n I plus 1. Okay. Okay. Okay, so this was unconditional. Okay. Permute, make a recursive call. Whatever it returns, add that to your count, local count. And then once again restore the array by a second swap. Okay. And eventually you return count. Okay. But now we have an extra check. So check whether AJ has already been put to the ith position. Okay, so for here I will use k equal to I, k less than j plus k if aj is equal to ak break. So I am searching. So if I look at this picture, this is I am considering something like this j, and your k runs from I to j minus 1. And I am comparing this with this, sorry, actually I should be here. I should be here. This is I, this is my j, and k runs from here 2 up to j minus 1. Okay. So I am trying to replace this or swap this with this. But before that, I want to make sure that this 9 has not appeared earlier. So I will make a comparison of AJ with AK, where K runs from I to J minus 1. right? K runs from I to j minus 1. If I see that aj has already appeared earlier, then I simply break. And if condition is never true, what is the value of j? K?
K equals
K equals j.
J minus 1.
J, right? K is equal to j if
Yes.
this condition is never satisfied. So this condition is never satisfied, so it is never explicitly broken, so it breaks when K becomes equal to j. Okay. So that way I can check if K, there are several ways you can do it. Maybe I can just say if K less than j, then continue. Do not do the remaining part. Or I can say if K is equal to j, then within a block, I will keep this. Okay, but this is also fine. If K is less than j, the loop was broken because of this explicit break statement, which means aj has appeared earlier, and then I will not do this part. I will simply go to the top of the loop. That's how continue works, right? So just tell me, this is fine or not? I will run it now. Happy? Tell something, yes or no?
Yes, sir.
Okay.
Yes, sir. Looks good.
Looks good. Let us see how it fares. Okay, cd. Parm general. Okay. Okay, so it's asking for how many elements. Let us maybe give 4, 8, 4, 3, 4. So it says something like this, 4, 8, 4, 3, 4. There are 20 permutations. So 4 appears 3 times, 8 once. So it is 5 factorial by 3 factorial. How much is that? 5 factorial is 120, 3 factorial is 6. 120 by 6 is 20. Okay, looks fine. And of course, this will also work for this case. 120 permutations as usual. 5, and if I say all are same, just one permutation. Yeah, this is fine. So it's 5 factorial by 4 factorial, that is 5. Okay. Happy?
Yes, sir.
Okay. So now this is a good, I never thought about this generalized permutation program, but thanks to some suggestions from you, I just worked it out. Good. This is a nice example demonstrating the power of recursion. Yeah.
Yes, sir.
Yeah, any question?
Sir, can you explain this logic, sir?
Which one?
Sir, which you have written?
This one.
Yes, sir.
Look, what I was doing up to this point, before index, I can hear some voice, but it's very, very low. I don't know. I think this is a good volume. Okay, so let me once again mention it, explain it. So the idea goes like this. Okay. So we have this original array of size n. So indices are from 0 to n minus 1. Okay. And let us say I have already taken care of the first I elements. And I want to permute for a fixed permutation that is placed here in indices 0 through I minus 1. I want to see all possible permutations of the rest of the array. Okay. And in all these possible permutations, if the elements ai plus 1, ai plus 2 up to an minus 1 are all distinct from one another, then suppose I have something like 2, 3, 1. This is what I have got, plus whatever I have got earlier that I am not going to change. Then what I will do from this part will remain the same, this part will remain the same, this part will remain the same, this part. Then what I will do, I will keep 2 here, 3, 1. This is my first recursive call. Second recursive call, I will swap 3 with 2 and make this recursive call. This is the second recursive call. Then I will swap 1 and 2. Then I will make the third recursive call. Okay. So recursive calls now get one extra value of I. So here I may be something. This is I plus 1. Okay. Now the difference from this with the earlier version is that it is now allowed to have repetitions in this part. Okay. So let us then see what happens if we have repetitions. Okay, once again think of this situation in the presence of a repetition. Instead of 2, 3, 1, I have, let's say 2, 3, 2. Okay. So from this, I will generate recursive instances. First part remains the same, second part 2, and then 3, 2. Then I swap 3 with 2, 3, 2, 2. Okay. Now earlier, since these elements were distinct from one another, I was also swapping this with this, okay, and trying to generate more permutations. But now I see that these two and these two, they are essentially the same. So if I bring these two here, what is the problem, sub-problem I generate? This is 2, 3, 2. But this is already covered by this. This and this, they are basically the same. So if I make a second or a third recursive call after swapping this with this, I am essentially making a duplicate printing and counting of the permutations, this fixed and 2 at this position. Okay. So before swapping a new element from somewhere later with the ith element, I first check whether that element, this is my AJ, has already appeared earlier from location I to j minus 1. If it is so, then I will not make the swap of AI with AJ, because that will lead to duplicate counting and duplicate printing. Otherwise, if I see that I have found a new element, for example, if the rest of the array is something like this, 2, 3, 2, 2, 4, 3, 2, then of course 2 I will do, 3 I will do, but this 2 has already appeared, so I will not make a recursive call on this 2, not a recursive call on this 2, but here 4, it's a new element. 3, once again, I have already done, so I will not make a recursive call. 2, once again, it's done. Okay. So I will make 3 recursive calls instead of 1, 2, 3, 4, 5, 6, 7. Okay. Because these 2 and these 2, they are identical. These 2 and these 2, they are identical. So if I put these 2 in the first position, or these 2 in the first position, or these 2 in the first position, or these 2 in the first position, it doesn't matter. They will generate the same list of permutations of the remaining part. Likewise, these 3 is identical with these 3. So it doesn't matter whether I swap these 3 with 2 or these 3 with 2. I will do it only once. First time, 3 appears. So in this code, this part essentially finds out whether I am trying to swap AI with AJ, make a recursive call, and once again revert back the array to its original composition. Okay, the same swap. And but before doing that, I just check whether this AJ has already appeared. Okay, like when I am here, I will just check whether 3 has already appeared. I will start search from here and end here. And here I see that 3 has already appeared. Okay. So that means putting 3 in the first position is already considered. I once again do not have to put 3 again in the first position and repeat the same stuff. Okay. Therefore, if I already find a repetition, then this loop is broken explicitly at some value of k less than j. So after the, or if there are no repetitions, for example, in the case of 4, okay, 4 is not equal to 2, not equal to 3, not equal to 2, not equal to 2, then it's something like this. Then for k equal to j, this continuous statement will not be executed. Then I will do this recursive call. Swap, make a recursive call, swap back. Okay, yes or no?
Yes, sir.
Okay. Yeah, I think it will take some time for you to absorb the exact, what should I say, the recursive paradigm. Okay, it's not like you are making Fibonacci number computations by making recursive calls. These are far more subtle than that. Okay, so I will give you a couple of more examples. Okay, maybe the first example is slightly easier. Okay, so once again, let me recall this binary search. So far, we have seen just an iterative version. Now I will do some kind of recursive version. So the input is a sorted array. Something like 5, 8, 9. There may be repetitions, 9, 12, 16, 17, 21, let's say. So it's a sorted array, let's say, of integers. It can be any other thing which can be totally ordered. Okay. And now I want to, so this is index 0, 1, 2, 3, 4, 5, 6, 7. So it's important to note that binary search does not make any sense unless we have a sorted array. Okay. So then I say, I want to find out whether 15 exists in this array. This is my query, the standard search query. So one possibility is I start from this, match 5 with 15, no, 8 with 15, no, 9 with 15, no, 9 with 15, no, 12 with 15, no, 16 with 15, no. You may continue the search until the end. 17 with 15, no, 21 with 15, no, or you can stop the search as soon as you get a number bigger than 15, the search key. Okay. This is what is called linear search. And as this linear search algorithm implies is that the input is not needed to be sorted. Okay. But if I have a sorted array, I can do far better than linear search. In fact, we have seen a demonstration. So what I will do initially. Yeah, anybody wants to say anything?
So what do you mean by sorted array, sir?
Sorted means it's this is less than equal to this is less than equal to this is less than equal to this. Okay, so this is sorted array in the ascending or increasing, or if you allow repetitions, non-decreasing order. So once you move down the array, the things that you encounter never decreases. They are increasing, or at least they are constant. So they are ascending. So this is called a sorted array in the ascending or increasing or non-decreasing order. Okay. Likewise, you can think about an array like 50, 28, 19, 17, 17, 6. So this is an array sorted into descending or decreasing order. Okay, so is it clear, the meaning of sorted?
Yes, sir.
Okay. So given that this is sorted, I can do better than making a linear search or exhaustive search, if you want to call it. What I will do, initially my entire the search window is the entire of the array. Okay, so I will compute the index 0 plus 7 by 2, which is 3. Okay, so I will now compare this 15 with 9. 15 is bigger than 9. Okay, this implies that since this array is sorted in the ascending or increasing order, there is absolutely no point in searching 15 in the first half. 9 is already smaller than 15. The elements that appear before this 9 are even smaller, cannot be greater than 9. Okay, so I can completely avoid searching in this part. Okay, and I will concentrate on searching in this part. On the other hand, if we have searched for something like 6, and then I see this is 9, this is 6. Okay, then you can simply say that there is no point searching after this, because 6 is already smaller than 9 and cannot appear after 9. Okay, So based upon this, I would say single comparison, you can discard one half of the array, either the first half or the second half. And you keep on doing this until the search window reduces to a single element. Okay, so we have seen this, an iterative version of this binary search. Okay, so I will now write the same search function in a recursive manner. Okay, and let's say n equal to 10, a equal to, let's give some fixed thing, 3, 5, 8, 14, 16, maybe 16 one more time. How many? 1, 2, 3, 4, 5, 6, 21, 25, 32, 35, 40. And I will search for some key X. There are 10 of them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, this has become 11. Okay, let us drop one, maybe 35. Okay. Okay, in general, actually, I should read this array from the user. But anyway, let's work with this fixed array. Scanf %d and x. This is the key. Okay, maybe I'll just print this. Okay. Then I will say b search or bin search, whatever. A X. Let us say that if it will return 0 or 1. Okay, b search. Okay, so I have to write this function. So it will return an integer value, b search IC. Okay.
Sir, is B search already a library function in C?
No.
In my code editor, it is giving suggestion for B search.
Then use some other name. I hope.
Okay, sir.
If it is already there, then compilation will complain. Let us see. No, I have to do one more thing. I am searching for A in X, and the current window I have to specify 0 to n minus 1. Okay, if it is there, I will just change the name. I'm searching for X, int L, int R. The current search window is from L to R. Let me see if the search is already there. I have to change the name. Previous declarator was here, external void star b search, okay. Then let us call it bin search. Okay, good. Oh, so b search is already there. Okay. So this recursive function takes an array. I do not need to pass its total size. Instead, I am just mentioning search from index L left end to index R the right end, and I am searching for X. From main, I am calling it as bin search AX 0 n minus 1. Because initially I have not compared anything and the entire array is my search window. Okay. So here I first compute. Okay. First of all, every recursive function has one case to terminate recursion. So that is when the window size is just 1. Then I will just check whether X is equal to AL. Then I will return 1. Otherwise, I will return 0. So this is what is called the basis case, induction basis. When the window size has reduced to 1, I will simply compare X with AL. Okay, L and R are basically the same at this point. If there is a match, I will return 1, which means yes. Otherwise, I will return 0, which means no. Okay. Otherwise, what I will do, I will compute left plus R over 2. Now, if I see that X is less than equal to AM, then what should I do? I will make a recursive call on AX. You tell L, X is less than equal to M, so there is no point searching in the bigger half. Okay, so but equality is still possible, so I will search from L to M. Else bin search A X M plus 1 right. Okay, but the point is that this function is also supposed to return something. Okay, so what I will do, instead of simply calling this, call this and return whatever value is.
Sir, here what is L, R, and M?
L is the, okay, so you have a search window, right? So L is the, initially this entire array is your search place. So L is 0, M is n minus 1. Okay. Then by making a simple comparison, you are reducing the size of the search window by a factor of 2, right? Okay.
So left and right, and you're splitting it into
Left, right, and M is the middle part, middle index. Okay. L and R is the current search window, I mean, boundaries. M is the middle part. By making a single comparison, I am changing the search window from L, R to L, M or to M plus 1, R. Okay. And this thing returns either 0 or 1. I will simply forward this return value to the caller, whoever calls me. Eventually, this is the outermost call in the main. Okay. If it returns 1, or anything non-zero, I will say found. Otherwise, I will print not found. Okay. So let me compile. Okay. So the array was what? Okay. 3, 5, 8, 14, 16, 16. Let us see. Which one? Maybe let us search for 23. Not found. There, if I search for 32, found. Okay, so what I will do, for each invocation, I will write this LR. Let us write it, then you will understand how this L and R evolve. Maybe 32. So initially, this is 0, this is 9. The entire array is the search window. I am searching for 32. So I will just make 2 splits here. 0 plus 9 by 2 is 4. I am comparing the key is what? 32. 32 with 16. So I know 16 is smaller, 32 is bigger, so I can discard this highlighted part. So my search will now be concentrated to 16, 21, 25, 32, 40. So this is index 5, 0, 1, 2, 3, 4, 5 to 9. So that is precisely what happened. In the next recursive call, the window is 5 to 9. Okay. Fine. Then that recursive call computes the middle index as 5 plus 9 by 2, 7. So it makes this division 5, 6, 7 and 8, 9. And it compares 32 with 25. 25 is smaller. So the 16, 20, 25, this part can be simply ignored. And the search can be restricted to this 32, 40. So index 8 to index 9. And this is precisely what happens here. 8 to 9. Okay. Then what I do in the third recursive call, or third recursive call, the middle index is computed as 8 plus 9 by 2, which is 8. So this is index 8. Okay. So now this is the search window 8 to 9. I compare the middle index, which turns out to be same as this. So I compared with 32. This is satisfied, x is less than equal to n. So I will not go to the larger half. I will go to the first half. So this becomes 8. R also becomes 8. Okay. So now this is the case of recursion termination. Because L has become equal to R, I will simply compare X with AL or AR. They are both the same. In this case, they are equal. So I am returning 1. Otherwise, I am returning 0. And whatever I am returning in this invocation, this will simply be forwarded, okay, by the calling function to the called function. Sorry, to the caller function. Okay. So this will return 1. This 1 will come to this function and will simply be forwarded to this function. This will also forward this 1 to this function. And that invocation happens to be this one. So it will now see 1. So it will print found. And let us see what happens if I just search for 23. Okay. Once again, you see 0 to 9, then 5 to 9, then 5 to 7, eventually 7 to 7. So you just work it out that this is what this should go on. And what is the seventh one? 0, 1, 2, 3, 4, 5, 6, 7. Now, sorry. 23 is compared with 25. Okay. This is not equal. So 0 is returned. So it will send this 0 to the caller function, which is this. This will forward to this. This will forward to this, but this is what is this binary search. It eventually gets the value 0 and prints not found. Yeah, tell. Of course, we could have done it in non-recursive manner, but this is just a demonstration of recursion. Yeah, tell. If you have any queries pertaining to this binary search, recursive version.
Sir, we are taking L and R values here that are not in the array. So when L and R is becoming equal, won't that be a problem? If there comes, I mean, we type something like 40, we want to find 40, and at last it is taking mean value no, by 2, M is equal to L plus R by 2. If it comes like not some number that
Okay.
is not in the array, then
okay, not in the array, but let's say it's even bigger than 40, 45. Then what will happen? What will happen is that initially this is the entire search window, 10 elements. Okay. By making a comparison, it will be something like this. This half will be eliminated. And then maybe the search will be restricted to this, then eventually to this. Then a comparison is made between 40 and something like 45. Let us see. 45, I want to find. 0 to 9, 5 to 9, 8 to 9, eventually 9 to 9. Then 40 is compared with 45. No match. So not found. Likewise, if I search for something which is too small, like 1, it is 0 to 9, then 0 to 4, 0 to 2, 0 to 1, eventually 0 to 0. Now this is a single element. So that 1 is compared with 3. Okay. Match doesn't occur. So 0 is returned. On the other hand, if I searched for 3, exactly the same thing would happen. 09, 09, 04, 04, 02, 02, 01, 01, eventually 00. But now the comparison is successful, so it says found. Here the comparison is not successful, so it says not found.
Hello, sir.
Yeah.
Sir, at the end, how L and R becoming equal, sir?
Because you see, this is 0 and 9. 0 plus 9 by 2. It is roughly M. So it will be either L to M or M plus 1 to R. So there are roughly half elements from L to M, and the remaining half elements are from M plus 1 to R. Okay. So every time you are reducing the size of the search window by a factor of 2, definitely if the current search window is not an even number, then you may have floor or ceiling. So if you keep on reducing thing by 2, and maybe you take ceiling, that doesn't matter, like this, 0 to 9, 0 to 4, 0 to 2, 0 to 1. Okay, every time the ceiling thing happens, eventually it will reduce to 1, right? How long can you keep on dividing things by 2? And okay, because you see, the search window size is 9. Then it becomes 5, 0 to 4, 5 elements. Then it becomes 3. Then it becomes 2. Then it becomes 1. So eventually search window size will collapse to 1. This is bound to happen, whatever the initial value of n is. No? Have you got your answer?
Yes, sir.
Good. So any other query pertaining to this? If not, I will just take a 5 minutes break, and then I will study. We will have a very complicated thing. Tell.
Sir, will you upload these codes, sir, in website?
These codes, of course. I always do it. After the class, I will upload all the codes. Okay, so then let us have a small break. I will come back in 5 minutes.
R main was void. So we will resolve that too. That again, if you remember the lines from the character.
Okay, so was there any query? Hello? Yeah, I am back. So have you raised any query? Okay, so I am back. So we will look at a third example of recursive functions. And this is, I believe, the most complicated example of today's set of examples. So that is what is called the tower of, sorry, let me just delete. The Tower of Hanoi problem. Okay, so this goes like this. There are three pegs. Peg number A, peg number B, and peg number C. Okay. So there are n disks initially sitting on the top of one another. So let's say this is of length 1, 2, 3, up to length n, n minus 1, n minus 2. Okay. So this is the initial configuration. Okay, so this is the init. Now your task is to move all of these n disks from peg A to peg B. You can make use of the peg C. So let me be more precise. Okay. So the task, move all the disks from peg A to peg B. Okay, so this is the overall task. Restrictions. You can move only one disk at a time. Okay. Second, you can never put a larger disk on the top of a smaller disk. That's basically this thing. And then, of course, what you can do, use the 3 pegs in any manner you like, subject to these restrictions. So at the end of this, I see. At the end of this procedure, the entire thing, that is n, n minus 1, n minus 2, blah, 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 up to 1, everything will be in peg B. Peg A and peg C will be empty. And in each move, you can only move only one disk. Okay, also what is one disk? Okay, so that's also something I have to specify here. You can move only one disk at a time, but which one disk? One disk at the top of a peg. Okay. So for example, you are not allowed to, let's go to the previous page, minus, okay. You are not allowed to move n and put it here, then n minus 1 you put it here. So at this initial configuration, the only disk that you can move is 1. You may put it from here to here or here to here. If you put 1 from here to here, okay, let's say, then you can move 2 disks, either this 2 or this 1. Okay. But if you choose to move this disk 2, then you cannot move it to the top of 1 because 2 is larger than 1. But you can put 2 here. Is that clear?
Yes, sir.
Okay, good. So this way, eventually you have to manage moving all of these n disks exactly in the same sequence, 1, 2, 3 to n minus 2, n minus 1 up to n in this peg. And at that point of time, C will be empty, A will be empty. Okay. So this is the problem. So let me first understand that you have no, I would say, no confusion about the problem.
Sir, I have one question.
Yeah, sure.
Sir, suppose I initially move one peg from A to C, suppose,
Okay.
and then from A to B, like, can I put it back? Like at any point of time, can I put the peg back
Yeah, you
to
can
A
put it back. You can put
if
it
it
back.
aligns with the restrictions?
Yeah. So it doesn't. Okay. You can move from one from here to here, and once again move it back from here to here. But why will you do it?
No,
Because
sir, not like that. I was thinking like I'll put one in C, then two in B, then one on top of that two in B, then three in C, then one back to A, then two in top of C, and then like
Yes. This kind of things you can do. The only restriction is that you can move only one disk at a time, whichever is sitting on the top of a peg. It may be here. This is currently empty, but if B contains certain things, you can move this top thing. Or if C also contains certain thing, you can move the whatever is sitting at the top. Yeah. So one of the top disks you have to move, but wherever you move, if you move this top from here to, let's say, B, whatever is sitting there should be larger. Okay.
yes, I got it.
Okay. So that is the problem statement. So first of all, in order to solve this, I need to have a recursive formulation of this in terms of this number of pegs n. Okay. So this is what I start with.
What we have to find? Number of steps.
How you do it, the exact movements, which disk you are moving from where to where, and eventually the total number of steps. Okay, how you achieve this, and in how many steps. Where a step is just step or move, which is just a movement of one disk from the top of one peg to the top of other peg. Okay, only one disk at the top of a peg at a time, of course, and this will also go to the top. Okay, so move something from the top of a peg to the top of another peg. Okay, you simply cannot put or move a disk to somewhere below the top, from top to top. Okay, this won't be allowed. Okay, so let's first make a recursive permutation. Something like this. This is your initial configuration.
Sir, how did we identify that this could have a recursive solution?
That is basically a matter of practice. Okay. And I would say it's a kind of hunch. Okay. Also, there are certain theoretical things, but let us not worry too much about this because this is beyond the scope of, I would say, this course. A, B, C. So it's as if asking you the question, how do I know that for this proof induction will work? Similar kind of stuff. Okay. What I will do, I will solve a problem of size n minus 1. Okay. So what I will do, first, I will keep the largest disk here, n, and I will move 1 to n minus 1. To the third peg, C. Okay. And this will happen in a recursive manner. So that means if I can solve the problem for n minus 1, then I am trying to solve it for problem of size n. Then what I will do, so this is step 1. Recursively move disks 1 through n minus 1 to peg C. Happy? Then the next step is obvious. I will simply move this largest disk from A to B. Okay, and let's see what happens after this step. Step 2, move disk number n from peg A to peg B. Right, so this is allowed. Because this is empty, nothing is sitting there. So I am allowed to move this because this is at the top. I am allowed to move this from here to here. Since there is nothing sitting there, I can put n there. Okay. So after this, what happens? So it goes like this. After I do this, peg A becomes empty. Peg B contains the largest disk N. And peg C contains this tower 1 to n minus 1.
Excuse me, sir. Sir, in the problem you said that we can move one disk at a time, and you moved from A to C n minus 1 disk.
That is a recursive call, which will involve a sequence of steps.
Okay, okay, yes, sir, yes.
Okay, whereas step 2 is a single move. This is a single move of this largest disk from here to here. Happy?
Yes, sir.
Yes, sir.
Okay. And step 3. Now this is the largest disk. It is sitting on the bottom of this peg B. It will not interfere with any other movement. I can put anything on top of it because this is the largest disk. So once again, recursively move disks 1 through n minus 1 from peg C to peg B, but this time using peg A as the helping peg. Happy or not?
Yes, sir.
Okay, so this is the recursive formulation. But whenever you have a recursive formulation, you must be.
Hello, sir.
Yeah, tell.
Sir, you are removing the disk from top or at any position?
Yeah. Yeah. Yeah, yeah. From top to top. From top in one peg to another peg. Yeah. So, end of recursion, we must also clearly mention end of recursion, because without induction basis, you cannot, even if you prove induction, the inductive part of a proof, induction is not complete. So you must have some basis. So this is the case n equal to 1. Okay. So it's something like this. It's a very simple problem. 1, 1, this. Sorry. Sorry. A, B, C. So this is the end of recursion. Situation like this. And if the problem is n equal to 1, then it is very trivial. Simply move from peg A to peg B. Happy or not? So always be careful whenever you are writing a recursive function. You should have a way to end the recursion. It cannot simply keep on going on forever.
Sir, in our implementation, ABC will be 3 arrays, right?
No, not needed actually. If you look at this problem carefully, let me go. So it suffices to know. So this is the current problem, which is specified by n. The recursive problem is specified by the parameter n minus 1. Okay.
Okay.
And then here also the recursive problem can be specified fully by n minus 1. Of course, you have to mention which peg, A, B, and C. Okay. And this movement, so this is the step 3. In step 2, you simply know which disk to move, which is n. However, if at every point of time, if you want to see how this peg A, peg B, and peg C look like, then you have to definitely maintain 3 arrays.
Yes, for that I wanted to know, like, how will I exchange, like at every step these arrays will get exchanged, like A and C. When C is done, it will be stored in A and then in C, so on.
Yeah. So let me write.
How will it takes?
Yeah, let me write this code, then it will be clear. Okay.
Okay.
How it will be. Okay. So tower of Hanoi dot C.
Excuse me, sir.
Yeah, tell.
Sir, could you increase the font size in your terminal?
Okay. Visible? Or even more?
Sir, a bit more will be better.
This is fine?
Yes, sir. Yes, sir. Yes.
Okay, so I'll make this also bigger. Okay. stdio, stdlib, main, n. First read this n from the user. Okay, so somehow I have to give this peg A, peg B, peg C. So maybe let them be characters, code A, code B, code C. Okay. So what I will do, so I assume that the user enters a positive value. Okay. So let's not worry too much about the integrity of the user. Tower of Hanoi, size n, from peg A to peg B, using peg C as a helping peg. And I will store the return value in this n steps variable. And then exit 0. This is our plan. Okay. So I will write a function tower of Hanoi which is solving a problem of size n. The source peg is A, the target peg is B, and the helping peg is C. Okay. So what I will do, and it will return the total number of steps. Tower of Hanoi, problem size, int source. Sorry, this is not int. This character target, character via, give some name. So I always should have something like this for terminating recursion, which happens to be this case. Okay, if n is equal to 1, there is nothing to be done. Simply move that disk from this to this. Okay. That is n, which is actually 1. This is fine. N is 1 here. From, that is the source peg to the target peg. And since this involves a single movement, I will return 1. Otherwise, I will keep a count. Initialize to 0. Then I add 2. Tower of Hanoi. This time I am okay, no problem. Okay, so what is the first step? Yeah, let's see. Okay, what is the first step? This is step 1. I will move n-1 disks from source to via. Okay. Using the target as the helping peg. This is precisely this thing, right? I am using these as the helping peg, that is the via peg, and solving a problem of size n-1. Now the source is A, the original source. The target is via, and the via is target. Okay, so it is just like this. Then printf, move disk from this to this. In this case, it is the same n, move disk number n from peg source to peg target. So this is step 2. And finally, from peg C to peg B using peg A as helping. Okay. So I will say plus count because I have made a single movement. And finally, I will once again solve an n-1 size problem. But this time, let us see step 3 from peg C via to target using source as the helping peg. Via to target using SRC as the helping. And eventually return CMD. That's it. This is solve an n-1 sized problem. Then make a single movement of the largest disk. And once again, make a recursive solution of the n-1 problem. Okay, so that's it. Let us see what happens. Good. 1, simply move from A to B. 2, disk 1 from A to C. Disk 2 from A to B. Disk 1 from C to B. So this is something somebody suggested. Okay, if n is 2, it's something like this. If n is 3, something like this. If n is 10, It's a huge sequence of moves. Okay. If n is 20, move. Oops. So this is the total number of steps. There are two questions. First of all, did you understand the logic? And second, do you guess what is the number of steps as a function of
2
n?
power n minus 1.
2 power n minus 1.
2 power n minus 1. Okay, so 5, 31 to power 5 minus 1. And if you want to visualize how the pegs look like, then you have to maintain 3 arrays, source array, target array, and via array, and see what happens. Okay, so I am not doing it. If you are interested, you can just augment this Tower of Hanoi code for a visualization thing. Okay. Okay.
Could you explain the logic once more?
Logic once more. First of all, are you with me when I say I want to solve this problem in this manner, in a recursive way? First, forget about the nth disk, largest one. Solve the problem of size n minus 1. But you do not move it here. Move it here, peg C. Okay. And like induction, recursion never fails. Okay. Only problem is that you have to ensure that there is an induction basis. And second, if something holds for n minus 1, you should be able to do it for n. So that is what is called the inductive part of the proof. So here what this procedure says, that if I can solve the n minus 1 sized problem twice, add to that a single movement, then I can solve the problem of size n. So this immediately follows from induction. Yes or no? If I can solve the problem for n equal to 1, and if I can solve the problem for n minus 1, then I can solve the problem for n, which means that I can solve the problem for all n greater than or equal to 1. Yes or no?
Yes, sir.
Yes, sir.
Good. So now, if you have faith in induction, have faith in recursion also. They are basically the same thing. Okay. So, but in order to make it work, I have to have an induction basis, which is this, n equal to 1 case. I have nothing to do, just move from A to B because there is only one disk involved. Okay. Otherwise, I will first solve the problem on the top n minus 1 pegs, move them from here to here without disturbing this n. Let it stay there as it is. Okay. Then I will simply move this from here to here. This is allowed because this is empty, so nothing is sitting there, so I can just put n, the largest disk, there. And then I am left with this situation. N minus 1 problem, which is solved already. And the nth one is now in place. Then if I can move this, and then just simply forget that n is sitting there. It is the largest one. It has no effect. You can put anything on top of it. Okay. And therefore, if you can move this n minus 1 things from here to here without disturbing this n, this time you have to use this as a helping peg. Then that is our desired final configuration. Okay. And this program precisely does that. This is induction basis. If there is only one disk.
Excuse me, sir.
Yeah.
Sir, movement at each step is top to top.
Top to top, top to top. Yes. Yes. Yeah. So this is actually, yeah, from top to top. Yeah, this is important. From top to top. Yes. Okay, so this is precisely what this does. If n is 1, the induction basis, move that disk from the source peg to the target peg. We do not have to worry about anything else. Otherwise, you first solve a n-1 sized problem. The source peg is source, the target peg is now via, and the via peg is target. Then you move the largest disk from source to target. Then from via to target using source as the helping peg.
Excuse me, sir.
Yes.
Sir, can you explain the code once again? Sir, at that time there was some network issue at my end, so I didn't understand properly.
Okay, so that's what I'm doing now. So maybe something like this. The user enters n and calls this Tower of Hanoi recursive function and stores the number of steps in this variable and then prints it. So that's fine. So the starting peg is A, the target peg is B, and C is my helping peg. This is the outermost call. Let me know if this is fine. I want to move all of these n disks from peg A to peg B using peg C as the helping one. Happy?
Yes, sir. So the
Oh.
function part.
Function. Now let us look at the function. So n is the size of the problem. This is the source peg. This is the target peg, and this is the helping peg, which I am calling via. Okay. Now once again you look at this end of recursion. If n is 1, simply move the smallest disk from here to here. Okay. So move disk from source peg to target peg and return 1 because this essentially is one movement. Otherwise, you simply say count equal to 0, or here you may say count equal to this anyway, it doesn't matter. Then this is the first step, step 1. From source to via, solve an n-1 size problem using B, that is the target peg, as the helping peg. Okay. So solve an n-1 size instance of the Tower of Hanoi problem. Source is source. Target is not this original target, but it is via. Okay. But in the process, I can use this B, the target peg, as the helping peg. Okay. Then it is our step 2. Move the largest disk from peg A to peg B, that is source to target. So it's exactly the same. Move the largest disk, size n, from source to target. And then since this is another move, I am incrementing count. Finally, I have to once again recursively move these n-1 things from here to here. But now this peg A is empty, so I can use it as the helping peg. So from via to target using source as the helping peg. Via to target.
Sir, hello, sir.
Yeah.
Sir, from C to A, we have to move n-2 disks because we have to put n-1 on B, sir.
Why n-2?
Sir, because we have to put n-1 on B.
1 to n-1? No. When you are
n-1th disk, sir. n-1th disk.
1 to n-1. Yeah, so n-1 disks. So that's what I am doing. n-1 disks from C, this is my C, to B, using A as the helping one. And when you are solving the second or the first recursion, the existence of n does not matter. It either sits here or here, but it is the largest peg. Whatever you put on top of it doesn't matter. Forget about the existence of this nth peg, nth disk, here or here. The largest one sitting at the bottom, you can do anything on top of it. Happy or not?
Yes, sir.
Okay. So that's precisely what is this does. Okay, so my suggestion is that you also find out how the different pegs look like after each movement, but for that matter, I have to maintain 3 arrays. Okay, so that's a little bit clumsy one, but anyway, it can be done. But this is the skeleton of all movement printing and the count of the count. In fact, if I run it with n equal to 2, this is the natural thing. Smaller one, for the moment, move to peg C. Bigger one, move to peg B. And then the smaller one is waiting at peg C. Move from peg C to peg B. Okay. For n equal to 2, this is the natural strategy, and that's precisely what we have done. But if you go to a bigger thing like n equal to 3, it may be a little bit difficult to show that this is the natural strategy. But mathematically, what it can be proved that this is the best way of doing it. You cannot do it faster than this. The number of steps has to be at least as large as 2 power n minus 1. And this program actually does it in 2 power n minus 1 steps. So it is basically an optimal way of solving this problem. You cannot do it faster. So, what do you think? Recursion is powerful, right?
Yes, sir.
Okay. And try to think why you cannot do it. In fact, this is evident from this. I would say, algorithm. At some point of time, you have to move this largest disk from peg A to somewhere else. And this is allowed. So you want to move this largest disk from this to somewhere else, which means nothing should be there on top of it, because you can move only the top one. Because this is the largest peg, wherever you are moving to, it must also be empty. Whether you are moving it from this to this, or from this to this, this to this, or this to this peg has to be empty. Otherwise, you cannot put the largest disk on the top of a smaller disk. So it has to be empty. But then this is just containing one disk, the largest one. This is empty. So the third peg must contain all these n-1 things. There are no other options. You have to proceed this way. Right? But anyway, don't worry about this mathematical proofs and all that stuff. Let us know whether this program is fine. You understood it. Okay, I will anyway upload all this codes in the course web page after the class. And if you are very interested, then you just add these 3 arrays and their respective sizes and all that stuff, and print how the 3 pegs look like after every move. Okay. Okay, so if you do not have any further question, we can stop here today because it's past 5. Maybe tomorrow I will tell a little bit about how computers handle recursion. Yeah, tell something. Are we done today?
Yes, sir.
Sir, what will be the pattern of Monday's test? Sorry, Tuesday test.
Pattern. Actually, we have not thought about it very clearly, but it may be something like this: fill in the blanks, writing small functions, or full main function or other functions, or some snippets, and there may be a few multiple choice or single line questions. Overall pattern will be roughly the same, but in that short test we didn't ask you to write any, independent code. This time we may ask. Yeah, that's it.
Sir, even if not for evaluation, can we get the marks of the short test just to see how we fared?
I think it is already uploaded. We asked the TS, and my TS said that they have completed it. So you can go to Moodle and just check. It should be against your name.
Sir, it says review not permitted.
I see. Okay. I will change the setting. Okay, or better, this is not my private course, so I will talk with the other teachers, and if they feel that review may now be permitted, we will do it. And if my other teacher says that let us hold it for some time, then we will hold it. Okay. Yeah, I now remember. Yes, this is, you are not permitted to look at this review. True. Yeah, so any other question?
So the syllabus for the mid-semester test will be up to.
Syllabus, I already told, this is up to functions, but without recursion, because all the sections didn't cover recursion. We have started it, but finished today. But anyway, a few issues still remain.
Sir, may I leave, sir?
Yeah, so let's say, may I leave? Are we done?
Yes, sir.
If there are no questions, we can leave. No problem.
Okay, thank you, sir.
Okay.
Thank
So
you, sir.
bye. See you tomorrow.
Thank you, sir. Thank you, sir.
Yeah. So see you tomorrow.
Thank you, sir.
Excuse me, sir.
Till
Sir, can we write a code to count number of circular permutation with
Of
repetition, sir? Without repetition, we can use.
Of course you can. Why not? What prevents you from doing it? Think how to do it.
So I don't know how to do circular permutation with repetition.
Circular
It was
permutation.
not in our syllabus.
Yeah, circular permutation. So
With repetition, sir.
Circular permutations. Yeah, so you think about the logic, I will also think. Circular, yeah, we will think, we will see. It can be done, not very difficult issue.
So maybe we can discuss it tomorrow after class if we have some time.
Tomorrow. Let us see then.
After class.
Okay, okay. We will think about it. I will think about it.
Sir,
We'll come
repetition
up with
case. Non-repetition, I think, we can implement form.
What?
So with repetition case.
Circular permutation with repetition.
Yes, sir.
Okay, let us see. Yeah. With and without repetition, both. Yeah.
Okay, sir. Thank you.
Yeah. Okay, so let me stop this recording.